Go
Morning,
ahead.
sir. Morning, teachers. Our topic is planes in 3D. Our presenters are Miss Bibi, Miss Marlowe, Miss Kelly is not here, Miss Romulus is not here, myself, and Sir Jonathan. Objectives: definition of a plane in three-dimensional space, vector equation of a plane, scalar equation of a plane, parallel planes, intersecting planes, angle between planes. Definition: what is a plane? A plane in three-dimensional space is a flat two-dimensional surface that extends infinitely in all directions within three-dimensional space. As you can see in the diagram here, what we're talking about. Defining a plane. A plane can be uniquely defined if, one, a point on the plane is known as P to O. We have X to O, Y to O, Z to O. Two, a normal vector to the plane is known as you can see the vector notation there over the symbol n, is equal to, you can have A, B, C.
Just pause. Can somebody erase this annotation that you see on the screen?
Sir Darius, you'll have to erase it.
Okay, miss, I will try.
Whenever you have, let's say, okay, P with a little O on the bottom is P subscript 0 or, right?
Yes, sir.
X subscript O, not to the, it sounds like it's a power you're talking about, right?
Yes, sir. Yes, as you can see in this diagram here, we have the normal vector is perpendicular to every line to the plane. As you can see there, note, a vector is a quantity that has both magnitude and direction. In 3D, vectors are written as you can see the vector there is equal to A, B, C. Position vectors, we know that position vectors, it starts from the origin. As you can see the definition here, it says position vectors represent a point in a space starting from the origin. Now we're going to go on to the equation of a plane, and we're going to look at two types. One, the vector equation of a plane, and the other one is the scalar equation of a plane. So let's talk about the vector equation of a plane first. So if vector n is normal to the plane and p subscribed p is any vector on the plane, and we have the vector notation there, is equal to 0. And it must be perpendicular to that vector. For the scalar equation of the plane, we derive from a dot product. When we work out all of these here, the standard form we have is ax plus by plus cz plus d is equal to 0. What is d? D is any constant to represent. So note that when we know the scalar equation of a plane, we automatically know it's normal. It is given by the coefficients of x, y, and z. The normal to the plane, 3x plus 2y subtract z is equal to 10. In this case, is 3x here. The coefficients are 3, 2 for y, and for z, it's a negative z, so we have -1. I will now hand you over to my next colleague who will take you through an example on these equations of the plane.
Good morning, everyone. So I'll be taking you through the example of an equation of a plane. So we're given point P, and the coordinates for point P is 2, -1, and 3. And our normal vector n is 4, -2, and 5. Now we have to find the equation of the plane that passes through P and has a normal vector n. So we can use the general equation of a plane given a point and the normal vector. So the general equation we have is a into x minus x naught plus b into y minus y naught, and c into z minus z naught, which is equal to 0. So we can substitute the values for this. So we know that a, b, and c would be our the values from our vector n, and x naught, y naught, and z naught would be from the point P. So we plug in those values into the equation. We'll have a, b, and c would be 4, -2, and 5, and we have x minus 2. 2 here would be x naught, and then y minus y naught is -1. So because we have 2 negative, we'll end up with y plus 1. And then we have z minus z naught, and z naught is 3. So we substitute that value there, and then we simplify. So when we simplify the equation, we'll end up with 4x minus 2y plus 5z equal 25. And that there will be the equation of our plane. Now we have a diagram, as you can see. The plane is shaded in the light blue, and we have our point P that lies on the plane, also marked in blue, and then the black arrow that is coming out from the point represents the normal vector, which is vector n. I'm not seeing the screen anymore. Sir, please give us a minute. Miss is saying that her connection just failed. Okay, so I was here at the diagram explaining the plane. So we have the plane, our point P, and then our vector here, our vector n. Next slide, miss. So for another example, we have another example here. We're given the point 1, 2, 3, and the normal, which is 2, 1, 4. Again, we use the general equation here. We substitute the values, and then we expand the brackets, and then simplify. We'll have 2x plus y plus 4z minus 16 equals 0. And that would give us the equation of the plane.
Yeah, either point or annotate on the diagram, so we on the slide, so we know where you are as you go along, right?
Okay. Good. So I was saying that this here would be our equation. We do the same thing and substitute the values and expand the bracket, then simplify, and got our equation here. So for the diagram, again, we have our plane, which is shown in blue here, and our point, and then the vector line, which is in black as well. Next slide, please. Good. Now, what if we're not given the normal vector, but we're given 3 non-collinear points instead? How do we find the equation of the plane? So if we're given 3 points, we use that 3 points, and we'll form 2 other vector, which would be vector P1, P2, and vector P1, P3. And then we find the cross product of those two vectors, which would be a vector perpendicular to both of them, and therefore it will be perpendicular to the plane. And we will consider that will be considered as our normal vector as well. So for this example, we have find the equation of the plane that passes through the points, and we're given 3 points here, P1, which is 0, 1, 1, P2, 1, 0, 1, and P3, 1, -3, -1. Now to find or form two vector, which is P1, P2, we use P2 and we subtract it from P1, and that we subtract the values. So when we subtract the x value, we'll have 1, -1, 0. And we do the same thing here for P1, P3. We use the point P3 minus P1. So we'll have the x value for them. The y value, we subtract them, and then the z value. And we'll have 1, -4, 2. So now that we have these two new vectors, we're going to find the cross product of those two. So to find the cross product, we set it up as a 3 by 3. Excuse me. And then I have a little working. I decided how we find that. So for I, we'd use -1 minus -2. Sorry, times -2 minus 0 times -4, which would give us 2 minus 0, and that would be 2. So we'll have 2i plus, for j, we'll have 1 times -2 minus 0 times 1, which would be -2 minus 0, which would be equal to 2. And then for k, we do the same thing as well at the bottom here. We use the value. So now these values that we have here, as Sarah was saying earlier, we use the values alone. So we have 2, 2, and -3. And that would give us the vector n. So again, we use the general equation. We substitute the values. Now that we know what is vector n, we can use any one of the points. So I use point P1 here, and I have n is equal to 2, 2, -3, and point P1, 0, 1, 1. I substitute that into the general equation and simplify, and I'll have 2x plus 2y minus 3z plus 1 equals 0. And that would be my final equation for the plane. On the diagram, it shows how a plane can be determined by 3 non-collinear points. The shaded region is the plane we constructed from the 3 points that we have. I also have another example worked out here where we are given, go back. Yeah. So for the other example here, we're given 3 points again, A, 1, 2, 3, B, 4, 0, -1, and C, 2, -1, 2. So we are using these points, and we're going to find 2 vectors in the plane, and that would give us, we'll find vector AB and AC. So that will be B minus A and C minus A. So when we subtract the values, we'll have for AB 3, -2, -4, and AC will have 1, -3, -1. So then we use those two and we find the cross product. When we work out the cross product to find the I component, J component, and K component, we'll have n would be equal to -10, -1, and -7. So then we can write the equation of the plane using the general formula, and we can use point A. So we substitute n and point A into the formula, then we expand. When we expand, we'll have negative 10x minus y minus 7z plus 33 equals 0. So what we can do is we can multiply both sides by -1 to make the x coefficient positive. So then we'll have our equation as being 10x plus y plus 7z minus 33 equals 0. Or we can rewrite it as 10x plus y plus 7z equal 33. And that would be the equation of the plane passing through the point 1, 2, 3, 4, 0, 1 ABC. So yeah, that's it. I'll now hand you over to my next colleague.
All right, good morning, everyone. I'll be handling parallel planes. So with parallel planes, we're dealing with two planes that never intersect, no matter how far they extend, because they have the same normal or the direction perpendicular to the plane. So some characteristics of parallel planes are they have the same normal vector. The two planes are parallel if their normal vectors are equal or having the same value, or their scalar multiples of each other. So for example, let's say our values might be 1, 2, and 3 for one of the vectors or the first plane. The second plane will be something like 2, 4, 6. So those would be, for example, those would be coordinates for A, B, and C. So they would have the same vector, the same normal vector, and that would therefore tell us that they're parallel. So the two distinct planes are parallel if n1 and n2 are parallel. Next slide, please. Right, so let's work an example where we can figure out if the planes are parallel and whether they're the same or distinct. So we have the example of plane 1 being x plus 2y minus 3z equals 4 and x plus 2y minus 3z equals -5. So we identify firstly the normal vectors. So from the standard formula we would use, the normal vectors would be A, B, and C. So plane 1 has a normal vector of 1, 2, and -3. And plane 2 has the exact same values of 1, 2, and -3. So since they are equal, the planes are parallel. And in this case, they're in exactly the same direction. So we have to figure out if the planes are the same or they're distinct. Now plane 1 has a D value or a value of 4, while plane 2 has a value of -5. Now since that side is the same, since the normal vectors are the same, but the D values are different, we say these planes are not the same. Therefore, that's why we have the term distinct. So therefore, these planes are distinct because they have a differing D value, but they're parallel because the normal vector is the same. Here we would have a diagram there showing us that the planes are indeed parallel, but they're distinct, meaning that the two lines, they're not exactly the same. We have some points differing there. So the red line, as you can see, there's some space between the red line and the black line. So now we'll be working an example to further prove that if they're parallel and distinct, we would calculate the distance between them using our formula. So when we have our D points, we have a formula whereby we input the D points and we basically put in the original equation minus the as a denominator, the square root of that. And then we substitute our values. And this is it's basically Pythagoras theorem, except that we have C in there instead of having a square plus b square equals c squared. So we'd use the square root, and then we'd substitute in our values, and the answer that we have would tell us the distance. So this would be the our perpendicular distance between the the two planes. And next, well, Miss Kelly was supposed to do this part, but I'll go through it. So let's say we have a plane given our standard equation, and we have a sorting point, which is x naught, y naught, z naught. So this point P is an example of a point. And then we can now use the perpendicular distance D by simply substituting those 3 points, the original standard equation on top, and the square root of the squared terms at the bottom, A, B, and C. So using this formula here, it's another method that we can find. This is a distance from a point on the plane. So it's not too dissimilar from the distance from a point to a plane, from a line that we used last semester. We're simply using back points, and we're using an updated form since we have a different type of equation here. The ax plus by plus cz plus d equation. So we have our plane being 2x minus 3y plus 4z equals minus 5. Minus 5 equals 0. That's our plane equation, and we have a point there, 1, 2, and 3. So for the numerator, we multiply a by the a, b, and c by the x, y, and z terms. And since d is a constant, that's not going to change. So once we put all of those values in there, and we find an answer, that becomes now our numerator. So here, in this example, we have a numerator of 3 after we've completed our calculations. So then we substitute for our denominator. We have a squared plus b squared plus c squared, and we square root everything. And we have a final answer there of the square root of 29. So now when we put our numerator and our denominator together, we have the answer, which gives us the perpendicular distance from a point to the plane. So as you can see from the diagram there, the second diagram mostly, you see point P being some distance there from that line. So the 0.557 is the distance between P and our plane there. It's not a large distance, it's a small distance. That concludes my part in the presentation. I will now hand you over to the next person.
Good morning, everyone. I'll take you through the intersecting planes and angles between planes. Now, when two planes are not parallel, then they intersect in a line. And to find the equation of a line, we need a point and a direction. The direction of the line will be perpendicular to both the normals N1 and N2. Thus, it can be found with multiplying the two normals. Here we have a diagram showing two intersecting planes, and when they intersect at a line. So we can see that planes P and Q intersect along the line M. We're going to take a look at angle between planes now, and then we're going to work examples. The angle between two planes is defined as the angle between their normal vectors. So let's say we have two normal vectors, N1 and N2. N1 is A1, B1, C1, and N2 is A2, B2, and C2. Then the angle theta between the planes is given by cos theta is equal to the absolute value when we multiply the two normals divided by the magnitude. We multiply the two magnitudes, which is N1 and N2, and we can see here that N1 times N2 is A1, A2 plus B1, B2 plus C1, C2. And the magnitude, we calculate that by taking the square root of each squared terms, A, B, and C, and we add them. So we have to note that we take the acute angle between them. So we use the absolute value in the numerator here. So we take in the positive acute angle. Here on the diagram, we can see that the two planes intersect, and these are the two normals, N1 and N2, and theta is between them, or the acute angle between the normals is what we want to find, or this is theta here. Example 1, we're going to find the angle between the planes P1, x plus y plus z minus 1 equals 0, and P2, x minus 2y plus 3z minus 1 equals 0. And then we are going to find their intersection. So to calculate the angle, the normal to P1 is N1, which is 1, 1, 1. You can see here from P1, we're taking the coefficients of the x, y, and z term. So that's the normal. And to P2, which is N2, will be 1, negative 3. Sorry, 1, negative 2, and 3 here. So therefore, the angle between them is, first thing we have to multiply to get the numerator. We're multiplying the two normals. So when we do that, we'll end up with a value of 2. So that will be our numerator. And the magnitude of N1, we calculate that here. That will be give us root 3. The magnitude of N2, when we use the formula and we calculate that, we'll have root 14. Now we're going to substitute into our formula. So N1 times N2, we see that we found that to be 2. And the magnitude, we have root 3, root 14. And when we do the calculation, we take the cos inverse of 2 over root of 42, and that will give us an angle of approximately 72 degrees. And that is that angle here between the two normals. You can see that the planes intersect, and we have the two normals, and it's highlighted in yellow. That will represent the 72 degrees here. Now we're going to find the intersections of the planes. Now the direction vector of the line of intersection is D, which is equal to, when we multiply the two normals, N1 and N2. So here we're going to take the cross product. So when we find the cross product, we see that when we do the cross product, we see that the direction vector of the line will be 5, negative 2, negative 3. Now we find a point on both lines. So to do that, we're going to set z equal to 0 for simplicity. So the first plane, x plus y plus 0 minus 1 is equal to 0. Therefore, this will give us x plus y is equal to 1. For the second plane, we do that again, x minus 2y plus 0 minus 1 is equal to 0. This will give us x minus 2y is equal to 1. Now we're going to solve these two equations. We're going to subtract them. So we have x plus y is equal to 1x minus 2y equals 1. This will give us x plus y minus x minus 2y, which is equal to 1 minus 1. Therefore, we'll have y plus 2y is equal to 0. This will give us 3y is equal to 0. Therefore, y is equal to 0. So now we're going to substitute y equals 0 into x plus y equal 1. And that will give us x equal 1. So when z is equal to 0, the point is 1, 0, 0. So here we can write the parametric equation of the intersection. So we're going to let the direction vector that we just found, we're going to let the direction vector be 5, negative 2, negative 3, and the point that we just found, 1, 0, 0, and we're going to write it in parametric form. So we'll have x is equal to 1 plus 5t. We're taking the 1 from the point and 5 from the direction vector, and t is a parameter. Then we have y equals 0 minus 2t, and z equals 0 from here minus 3t. To simplify it, we'll have x is equal to 1 plus 5t, y is equal to negative 2t, and z is equal to negative 3t. And here we have a graph showing the intersection of the two planes, the line at which they intersect, and the normal. Second example, we're going to find the angle between the planes 2x minus y plus 2z equal 3, and x plus 2y plus 2z is equal to 5. So the first thing we're going to do is to find the normal vectors. So the normal vector to plane 1 is the vector of coefficients 2, -1, 2, as you can see here. And the normal vector to plane 2, N2 will be 1, 2, 2. Now step 2, we're going to find the dot product of the normals. So we're multiplying the two normals. When we do that, we'll have a value of 4. The next step, we're going to find the magnitude. The magnitude of N1, when we substitute into the formula, we're going to have 3. And when we substitute into the formula to find the normal 2, N2, we're going to have a value of 3 also. So step 4, we're going to use the angle formula again. So the angle theta between the planes is the angle between their normals. So we use our formula cos theta is equal to the absolute value of N1 times N2 divided by the magnitude of N1 times the magnitude of N2. So when we substitute our values, we'll have 4, the absolute value of 4 divided by 3 times 3, and that will give us 4/9. The last step is to find the angle. So we take cos inverse of 4/9, and that will give us an angle of approximately 63.26 degrees. Here we have another example to find the point of intersection between the line x equal 1 minus t, y equal 3t, and the plane z equal 1 plus t, and the plane 2x minus y plus 3z equals 6. So we're going to substitute the parametric equations of the line into the plane equation to find the intersection. So we're going to substitute x, y, and z into the plane. When we do that, we'll have 2. That's 2 from the coefficient of x here, and x is 1 minus t, so that's how we have 1 minus t here, minus 3t plus 3 times 1 plus t is equal to 6. So we're going to expand. When we expand, we have 2 minus 2t minus 3t plus 3 plus 3t is equal to 6. Then we combine the like terms. We have 2 plus 3 plus negative 2t minus 3t plus 3t is equal to 65 minus 2t equals 6. Now we're going to solve for t. To do that, we'll have minus 2t is equal to 6 minus 5 minus 2t, and that will give us 1t is equal to a -1/2. Now we're going to substitute back t equal -1/2 into the line equation. And when we do that, we will have the points, our final answer, 3/2, -3/2, and 1/2. So this is the point of intersection between the line and the plane. And that has brought us to the end of our presentation. Thank you.
That's it?
Yes, sir.
Give me a second. I want to stop the